I guess we can now start. Um, so let me just try to share my slides. Okay, so I am now sharing my slide. So I hope you can see my slide now. Okay. Um, and I hope everyone can hear me well. Okay. If there's anyone who cannot hear me well, please try to call my attention as soon as possible. Okay, or you can also chat in the chat box. Okay, if you like. Okay, so I presume I'm okay for everyone. I don't see anything in the chat box. Okay, so start. Let us now try to discuss soil compaction. Okay, now soil compaction is very important when we try to do embankment works. Okay, for example, when we try to excavate for foundations. Okay, then we backfill the soil after constructing the foundations. Okay, so we need to compact them. No? So also in roads, okay, when we construct roads, then we also need to do the proper compaction. Okay, okay. So as you can see here in the slide, okay, in the construction of highway embankments, okay, earth dams and many other engineering structures, okay. Um, I think in Bohol, for example, there is a large earth dam there. I think in Bohol, for those of you who comes from Bohol, okay, I think you have a large earth dam there. Okay. And then, for example, in highway embankments, okay, um, normally these are highways, no, being constructed on elevated grounds, no, from the natural ground. Okay, for example, here in Luzon, okay, those expressways that you have heard of, going to the north or going to the south, for example, they were built on embankments. Okay, yeah, to try to elevate the highway from the natural ground, so that it will not get flooded, for example. Although there is some area now in the NLEX part, no, the North Luzon Expressway, wherein it got flooded. Okay, but yeah, that's the purpose of embankments. Okay, so when we create earth dams, okay, earth dams, highway embankments, okay, for example, and many other aspects of construction, when we encounter loose soils, okay, so these loose soils must be compacted to increase their unit weights. Okay, so compaction increases the strength. Okay, because when you have loose soils, usually the strength for these loose soils are quite weak. Okay, so we need to compact these loose soils so that they will become dense soils, no? Dense to very dense soils. So we don't like very loose to loose soils um, in the field. Okay, so we like dense and very dense soils. Okay, so again, compaction increases the strength characteristics of soils, which increases the bearing capacity of foundations constructed over them. In the case of foundations, okay. When we say foundations, Normally, we have shallow foundations. Okay, these are the ones that you have, for example, in your houses. Okay, we normally construct shallow foundations. But in critical structures, for example, such as the Cebu Cordova Bridge project, then we also construct uh, deep foundations, no? Such as board piles, okay, or driven piles, for example. So compaction also increases the amount of, um, or decreases rather, the amount of undesirable settlement of structures and also increases the stability of slopes of embankments. No? For example, in practice, normally we consider, say, for example, 25 millimeters of settlement criteria. So during calculations, when we see that the settlements would uh, go beyond the prescribed settlement criteria, then yeah, we recommend that okay, if we find loose soils there, then we recommend that they be compacted to reduce the settlement of the structure. Okay. So smooth wheel rollers, okay, sheep's foot rollers or rubber tired rollers, as well as vibratory rollers, okay, are generally used in the field for soil compaction. Okay, and then vibratory rollers are used mostly for the densification of granular soils. For example, um, sometimes we can use a 10-ton vibratory smooth wheel roller, for example. Okay, so because smooth wheel rollers can be static, it can also be vibratory. You just need to put some attachments no, to the rollers. Okay? But these equipments
Very
can
close to the
only
answer. In the
compact
columbarium out on the east
up
side of
to
Night City,
a
you can find several
maximum
newly added
depth.
grave sites for
Okay,
some of the notable
these
characters
equipments.
from Edge Runners.
Now,
When
when
you have a
you
weapon
try to
holster, you can
compact
now hold the D key
at
or
deeper
triangle
depths,
or Y.
okay, then we have what we call as a vibro float, no, devices, okay, which are used for compacting granular soil deposits to a considerable depth. Okay, so yeah, uh, say below 3 meters, for example, no? Okay, wherein it can no longer be um, excavated by normal backhoe equipments. Okay, normally for backhoe equipments, we can only excavate, say, around 3 meters. Okay, if you have that's the short arm backhoe equipment. If you have the long arm backhoe equipment, then usually we can still excavate, say, around 5 meters, six maximum. Okay. But beyond that, then you can no longer do excavations. Okay. Um, I mean, excavations from the surface, rather, no? From the surface. So, if you don't want to do that, then you have the option of compacting, considering vibro flotation approach or vibro compaction approach. Okay. So, we will discuss this in a while, no? These things. Okay, just to delve deeper into compaction, okay, let's try to have some um, basic understanding of the compaction mechanism. Okay, now compaction in general is the densification of soil. Okay, again, don't worry about the text here; these are all taken from your book. Okay, I just put them here for easy reference. So compaction in general is the densification of soil, okay, by the removal of air, okay, which requires mechanical energy. Okay. So the degree of compaction of a soil is measured in terms of its dry unit weight. Okay. So again, if you recall, we have the moist unit weight, you have the saturated unit weight, then you also have the dry unit weight. Okay. Now, when water is added to the soil during compaction, it acts as a softening agent on the soil particles. Okay? So here, during the addition of water, the soil particles slip over each other, okay, and move into a densely packed position, okay. So that means that we need to have some moist there, okay. Now, the dry unit weight after compaction first increases as the moisture content increases. It's also found in your book, okay. So here you have, uh, yeah, okay, you have the dry, okay. So here the dry unit weight, which increases as the moisture content increases. No? Okay. So for example, here at a moisture content of 0, for example, then if the moisture content is 0, okay, if you look at this graph here, okay, it is a graph between moisture content W and the moist unit weight gamma, no? Moist or total unit weight gamma. Okay. Now, when you say moist, that means there's some level of moisture there. But if the moisture content is 0, okay, then the moist unit weight at this level, okay, that's gamma sub 1, okay, will then be equal to the dry unit weight at a moisture content equal to 0. Okay, so that's this point here. Okay, so that's this one. No? Okay, so at the moisture content equal to 0, then the moist unit weight, okay, wherein when you say moist, there's some moisture in it, or there's some saturation, there's some degree of saturation in it. Okay, then that moist unit weight will be equal to the dry unit weight, gamma sub T, that's dry, okay, um, with this corresponding equation here now, which is now your gamma sub 1. Okay? Now, when the moisture content is gradually increased, okay, and the same compactive effort is used for compaction, for example, using the same equipment on site, okay, then the weight of the soil solids in a unit volume gradually increases. Okay. Say, for example, here at a moisture content W sub 1. Okay. So here, take note here, the moisture content is 0. Okay. Let's presume that this area here, in this area are, okay, the solid particles. Okay, this one here, then this one here, this region is the addition of the water. Okay, that's addition of water. So here, that means we are increasingly adding the water. Okay, so here you try to increase the water. Okay, then you compact, then you get a dry unit weight. Okay, yeah, and then you increase the water again, and so on and so forth. And then, for example, here at a W sub 1, at a particular moisture content, okay, this one here, okay, then you will have a, a, a corresponding um, a moist unit weight, okay? The corresponding moist unit weight, wherein this one here is now the change, okay? From this point up to this level here in the moist unit weight is now the change in the dry unit weight from the initial dry unit weight, at moisture content equal to 0, okay? Now, okay. So here you have now at the moisture content of W sub 1. Okay, so the moisture or the moist unit weight is now equal to gamma sub 2. Okay, so that's this one here. And then by equation, the dry unit weight at this corresponding moisture content is now given as the dry unit weight at the moisture content equal to 0 plus the change in the dry unit weight. Okay, after you extract the moisture content. Now, for example, you oven dry in the lab. Okay. Now, beyond a certain moisture content, say, for example, the moisture content equal to W sub 2, okay, any increase in the moisture content tends to reduce the dry unit weight. Okay? Now, this phenomenon occurs because the water takes up the spaces that would have been occupied by the solid particles. Okay. Now, in this case, the moisture content at which the maximum dry unit weight is attained, okay, is now generally referred to as the optimum moisture content. So if you look at the figure here, okay, at a certain moisture content, say now at W sub 2, wherein this is now the amount of what moisture content that you're adding, okay, um, from this amount of moisture content, okay. So then the change in the dry unit weight also increases, okay. Okay, so here it increases. I hope you're seeing my cursor. So again, here it increases until it will reach a point, okay, at W sub 2, okay? It will reach a particular dry unit weight in such a way that if you add more water beyond W sub 2 or the moisture content at 2, if you add water there, then the dry unit weight will then slowly decrease, okay? Yeah. Because on this region here, the water will already take up part of the voids that is supposed to be occupied by the solid particles. Okay, so that means that there's no more point adding more water, no, beyond this level. So in this case, when you now reach this point, then this one now is what we call as the optimum moisture content. Okay, and then this one here at this moist unit weight after extracting the moisture, okay, oven dry in the lab, okay, using the oven, okay, then you can derive the the maximum dry unit weight. So this one here, okay, so say this one here, okay, yeah, this one, then increase until such time you will get the maximum dry unit weight. So the goal then of compaction is to try to get the optimum moisture content as well as the maximum dry unit weight. Okay, so we need to have a graph, okay, something like this. Now we try to get a plot, something like this, in such a way that we can determine the optimum moisture content and the maximum dry unit weight, okay, to give us a certain uh, um, density of the material that we require, for example, in the field. Usually in construction, these are normally prescribed by the client, for example, that we require this amount of compaction, okay? It depends on the structure, okay? Okay, so are there any questions so far with this one before I proceed? Okay. So basically, this is the basic concept of compaction. No? Okay. Okay, so if there's none, okay, let me continue. Okay. 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 So in the laboratory, the laboratory test generally used to obtain the maximum dry unit weight of compaction. And the optimum moisture content is now what you call the Proctor compaction test, no? After this guy, Proctor in 1933. Okay. Okay. So here we have the standard Proctor, if you can see here on the right. Okay. We have here the standard Proctor test equipment. Okay. I hope you're seeing my cursor. Okay. We're in A here is now your what you call your mold. Okay. We call this the mold. Okay, in picture, this is now the one. This is now your mold. Okay, and then a B here is now your hammer. Okay, so this one here, no? This is now the hammer. Okay, don't worry, you will be doing this in the lab as well. Okay, so you can really do the compaction test yourself. Okay, so here we have the dimensions of the mold. Okay, um, the outer and the inner diameters. Okay. Then here you have the height of the mold. Okay. And then here you have the height, the drop height of the hammer. Okay. The diameter of the hammer, as well as the weight of the hammer. Okay. So that's in this case, that's at 2.5 kilograms. Okay. So take note for the Proctor test, we have what we call as the standard Proctor test, as well as the modified Proctor test, no, which differs in the dimensions of this equipment here. Okay, uh, just to have some difference in the compactive effort. No, we call it the compactive effort. Okay, okay. So with the Proctor compaction test, so for each test, the moist unit weight of compaction gamma, okay, can be calculated as the weight of the compacted soil in the mold, that's the capital W, divided by the volume of the mold. Okay. In this case, the calculated volume is about 944 cubic centimeters. That's basically I think this one here, the diameter, you get the area of this diameter here multiplied by the height. That gives you the volume. Okay, so that's this one. Okay. So now for each test, okay, the moisture content of the compacted soil is determined in the laboratory, okay, using the uh, um, oven, okay, using the oven. Okay. So once we now have a known moisture content, okay, then the dry unit weight can be calculated as gamma sub D, which is now equal to the moist unit weight. That's this one here, okay, divided by 1 plus the percentage of moisture content, okay, by doing that in the lab using after oven drying the sample, okay, the compacted sample, okay, then divide that by 100, okay, just to have it in decimal. So let's call this equation 6.1 and 6.2, okay? I don't know if it's still the same numbering in your book. Okay? Now, so the values of the dry unit weight derived from this equation can be plotted against the corresponding moisture contents to obtain the maximum dry unit weight and the optimum moisture content for the soil. Okay. Yeah. Okay. Now, so here we have the procedure for the standard Proctor test is given by ASTM D698. Okay. Or if you consider the AASHTO test designation, that is called AASHTO T99. Okay. This is usually the standard we use in practice. No? Okay. So here we have a plot, okay, an example plot of the compaction test using a standard Proctor compaction test. In this case, it is for a silty clay material. Okay, so I hope by this time you already know what we mean by silty clay, based on our soil classification. procedure. Okay. So here at the bottom, you have the moisture content. Okay. We plot the moisture content, and then here in this axis, we plot the dry unit weight no, after oven drying the sample. Okay. So then you plot this curve. Normally we try to get 5 points. Okay, say for example 1, 2, 3, 4, 5, for example. Then you try to connect the points. Okay, then hopefully you can get a nice curve. Okay, and then from this curve you try to look for the peak. And once you have the peak of the curve, then you project it down. That gives you the optimum moisture content. And then if you project it horizontally, that will give you the maximum dry unit weight. Okay. Now this plot here, okay, this plot um, should not exceed the plot for the zero air void curve. Okay. Uh, that means here you don't have voids anymore. No, that is well compacted. Okay. So that means you have a degree of saturation of 100%, okay, in this case. Okay, so there's no air. So that means all the materials is just comprised of the solids and um, water. Okay, so if you try to plot that curve, okay, that will give you this one, okay, for a particular specific gravity of a material. In this case, this line is for a specific gravity of 2.69. Then this curve here must not exceed this line. Okay, otherwise that would be an error. That there's an error in your test. Okay, because take note, this one here may not be 100% degree of saturation. Now, this may only be 80%, 90% degree of saturation. Wherein this one here is the plot for 100% degree of saturation. Okay. So again, if you try to recall, the degree of saturation is defined as um, 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 mm, yeah. So that's the uh, water content. Okay, so the degree of saturation is the water content contained in the voids. Okay, yeah, that's the degree of saturation. Okay, okay. Now, I would suggest that when you do this in the lab, okay, you will normally be grouped. Okay, you will normally be grouped. I suggest that the ladies, okay, the ladies, you try to distribute yourselves among the guys, no? Okay, because it's a bit um, mm, it requires some effort, no? To do the compaction test. No? Okay, okay, okay. Now, so for a given moisture content W and a degree of saturation, okay, S. Okay. Now, the dry unit weight of compaction can be calculated by this formula here. Okay. Um, so where the dry unit weight is given by the specific gravity of the soil solids multiplied by the unit weight of water over 1 plus the void ratio. Okay. Now, aside from this, okay, we try to recall from the previous discussions, we know that the degree of saturation multiplied by the void ratio is just equal to the specific gravity of the soil solids multiplied by the water content, okay, or the moisture content, okay. Um, so if you just transfer the degree of saturation here, so we now have the void ratio. substitute it in this formula, that gives you equation 6.3. Okay, that's for any soil. Okay. Okay. So for a given moisture content, then the theoretical maximum dry unit weight is obtained when no air is in the void spaces. Okay? In other words, when the degree of saturation is equal to 100%. Okay, such as this curve here. Okay, let's presume that this one here is 100% degree of saturation. Hence, the maximum dry unit weight at a given moisture content with zero air voids can be obtained by substituting a value of 1 for S in this equation. So we substitute 1 here. No? That's for a degree of saturation of 100%, or S equal to 1 when substituting in this equation. So in that case, we no longer have S in the equation. So that means here, if your S is now 100%, then we now call that unit weight as the zero air void, ZAV, the zero air void unit weight. Okay. And then just try to do some manipulations here. Then you get, or you do some algebraic manipulations here. Then you get this formula. So to obtain the variation of the zero air void unit weight with respect to moisture content, okay, then we first determine the specific gravity of the soil solids, okay, such as this one here. Okay, then we try to know the unit weight of water, which is that's given. Okay, and then we assume several values of the water content, say 5, 10, 15%, and so on. So such as this one here, 5, 10, 15, and so on. Okay. And then we calculate the zero air void for various values of the water content. Now, because this is known, that is given, or that is known rather, this one is known for a given soil material, such as this one here, that's known. Okay. So then, doing that, then we can now plot this theoretical zero air void curve for different moisture contents at a degree of saturation of 100%. Okay. So, okay. So again, under no circumstances should any part of the compaction curve lie to the right of the zero air void curve. Okay. So this one here is the compaction curve. We call this the compaction curve. Okay. So it should not exceed or it should not go beyond, or should not go to the right of the zero air void curve. Otherwise, if your plot is like this, sorry, if your plot is like this, it goes to the right of the zero air void curve, then there's an error in your test. Okay. For example, there's an error in the conduct of your test in the lab. And then you will have to repeat the test again. Okay. And please take note, you need to get about 5 to 6 points, and each point is not, it's quite tiresome to get. Okay, then after you get the last point, then when you plot, it goes beyond here, this line, then you have to repeat the process. Okay, yeah. So please make sure that you do the right approach, when you do this in the lab, so that you will not be tired, because it was tiresome. This was usually the most tiresome test in the lab that we do. Okay. Okay. So let's now try to consider the effect of the soil type, okay, with respect to the compaction curve. Okay. So for the soil type, okay, considering the grain size distribution, the shape of the soil grains, the specific gravity of the soil solids, and the amount and type of clay minerals present has a great influence on the maximum dry unit weight and the optimum moisture content. So I think these terms here, we have discussed them during our first meetings or in the previous meetings. Okay, so here we have four curves, four compaction curves for four different soil types. Okay, so for example, this one here is for a sandy silt material. This one here for a silty clay material. Okay, so this one here is for a highly plastic clay material, which we generally don't like in the field. Okay, and then here, this is a plot or a compaction curve for a poorly graded sand material, which we generally don't like in the field also. Okay, we always prefer um, low plasticity clays or silts or well graded sands, no, for example. Okay, in practice. Okay, but at least here you see the different plots for different soil types. Right? So don't expect that you will only get a curve like this. It depends on the type of soil material. Okay. So again, those plots there were done according to the standard Proctor test. Okay. ASTM D698. Normally, when we prepare geotechnical reports, for example, we normally put there the procedures that were being done both in the field and in the lab. Okay, and then we normally put the ASTM standards being used. Okay, so that whoever reads the geotechnical report knows that the preparer of this report, okay, the lab rather, where this report was based on, is using this standard. Okay, so then we automatically know how it was done. Okay, so for example, if you do ASTM D698 in the lab for your laboratory work, then you know that ASTM D698 or the standard Proctor test is how it is being done in the lab based on what you will be doing later on. I don't know if you have already done it, this, or if you have already done this already. Okay. Okay. So please take note that the bell-shaped compaction curve shown in the figure that we have just seen earlier is typical for most clay soils. Okay, so let's see. Okay, okay, so here, this one here, bell-shaped curve. No, the bell-shaped curve. Okay, that's typical for clay soils. Okay. Now, for sands, for example, in the case of sands, the dry unit weight has a general tendency first to decrease as moisture content increases, and then it will increase to a maximum value with further increase in moisture. Okay. Now, the initial decrease of dry unit weight in the case of sands, for example, with the increase of moisture content can be attributed to the capillary. No? That's the capillary tension effect when the soil is not yet fully saturated. Okay, so that's what you call a capillary tension effect, wherein the capillary tension effect happens when there is a combination of air and water within the voids of the soil. Okay. That's where we have capillary tension effect. Usually, we discuss this in very detail in the graduate degree, for example, no, in the master's degree, no, on the subject on unsaturated soil mechanics. Okay, but for the moment, let's just try to understand that for an unsaturated soil, okay, any soils below 100% degree of saturation, you have that what you call as the capillary tension effect, especially in the case of sands, for example. Okay. So at lower moisture contents, this capillary tension in the poor water inhibits the tendency of the soil particles to move around, no? And be compacted densely. Okay, so that's why when there is not enough moisture for a particular soil material, okay, then you cannot achieve, no, you cannot achieve the maximum dry unit weight that you desire or the maximum density that you desire. Okay, so that's why the amount of water content is that is added to the soil during compaction is very important. Okay, so if you go back to the figure, okay, so this initial decrease here in the dry unit weight, that's because of the capillary tension effect in the case of sands, for example, before the dry unit weight increases as the moisture content increases. Okay, yeah, okay. So that's the effect of the soil type. Okay. Now there's also what we call the effect of the compaction effort. Okay. Now before we go to the effect, then let's first try to define what we mean by the compaction energy. Okay. So the compaction energy per unit volume used for the standard Proctor test, okay, um, can be given by this equation here, okay, where the compaction energy is equal to the number of blows per layer, because you recall you have a hammer, right? Okay, so you do some drops there, number of drops, okay, so or number of blows. So you record that. You record the number of blows per layer, and then multiplied by the number of layers. Say, for example, you divide the mold into 3 or 5 layers, and then each layer you do number of blows, okay? Then multiply that by the weight of the hammer, okay? Multiplied by the height of drop of the hammer, depending on if you're using the standard Proctor test or the modified Proctor test, okay? Then you divide that by the volume of mold. Okay, so that gives you the compaction energy per unit volume. Okay, so in the case of the standard Proctor test, for example, wherein you have 25 blows per layer, then you try to do 3 layers, okay, 3 layers, okay, multiplied by the weight of the hammer, that's 2.5 kilograms. Let's see, is that correct? Okay, that's 2.5 kilograms, this one here, okay? 2.5 kilograms, just convert that to kilonewtons, okay? Then multiply by the drop of the hammer, which is 305 millimeters, okay? Is this correct? Okay, yeah, that's around 305 millimeters, okay? Okay, and then you divide that by the volume of mold, no, which we have just seen earlier, no? Okay, so then you now have in kilonewton meter per cubic meter. Okay, so kilonewton meter per cubic meter, that's now your compaction energy. Okay, so roughly about 600 kilonewton meter per cubic meter. Okay, that's the compaction energy for a standard Proctor test. Okay. 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 Now, if the compaction effort per unit volume of soil is changed, okay, for example, we increase the compaction effort, okay, then the moisture unit weight curve would also change. Okay, so not only with respect to the soil type, but changing also the compaction effort would also change the compaction curve. Okay, so for example, here, the compaction curves, no, for a sandy clay, for example, okay, for a sandy clay. So here, for the sandy clay, it for this plot, it has a liquid limit of 31 and a plastic limit of 26. Okay, so we see here that for different compaction efforts, by varying the number of blows. For example, say here for this curve one, you did 20 blows per layer. For curve two, you did 25 blows per layer. Then on curve three, you do 30 blows per layer. Then on curve four, you do 50 blows per layer. Okay. So here we see that if you increase the compaction effort, okay, the um, the the optimum moisture content, okay, the optimum moisture content seems to decrease. It seems to decrease as the compaction effort is increased, while the maximum dry unit weight is increased, uh, while the compaction effort is increased. Okay, yeah. So that's the effect of the compaction effort. Again, none of these curves should lie to the right of the zero air void curve. For example, for this sandy clay material, the specific gravity is about 2.7. Okay. Okay. So again, for that plot, there we use there the standard Proctor test. Okay. Okay. So again, here, as we have seen in the plot, as the compaction effort is increased, then the maximum dry unit weight of compaction is also increased. Okay, and again, as the compaction effort is increased, the optimum moisture content is decreased to some extent. So that's what we observed again. Where was that? Here, and that's what we observed. Okay. Okay, so these statements here are true for all soils. Okay, however, the degree of compaction is not directly proportional to the compaction effort. Okay, it's not directly proportional. Okay, okay. Now, the standard Proctor test was basically corresponding to a particular equipment in the field. Okay. Now, as time went by with the development of heavy rollers, okay, these compaction equipments were being improved. Okay. And their use in the field compaction, then the standard Proctor test was also modified in I mean the standard Proctor test in the lab was also modified to better represent the field conditions. Okay. Now this revised version is now referred to as the modified Proctor test as per ASTM B1557, or if you use the AASHTO such as the DPWH, they refer to the AASHTO. So that's the AASHTO T 180. Okay. Um, so in this case, in the conduct of the modified Proctor test, aside from the standard Proctor test, the same mold is used with a volume of 944 cubic centimeters. Okay, as in the case of the standard Proctor test. However, the soil is compacted this time into 5 layers instead of 3 layers by a hammer that has a that has a mass of 4.54 kilograms. Now compared to the standard Proctor test, which is about 2.5 kilograms. So this is heavier. Okay, the hammer is heavier. Okay, and then the drop of the hammer is about 457 millimeters compared to the standard Proctor test, which is about 305 millimeters. Okay. Now, the number of hammer blows for each layer is kept at 25, as in the case of the standard Proctor test. Okay. So for the modified Proctor test, if you follow the same formula here, Okay. Then the compaction energy will then be equivalent to 2,700 kilonewton meter per cubic meter as compared to the 600 kilonewton meter per cubic meter for the standard compaction test. Okay. So if we try to compare the two, okay, so this one here, the smaller one, is now the standard Proctor hammer, while this one here is the modified Proctor hammer. Okay, yeah. So that's the difference no, between the standard test and the modified Proctor test. Okay. Okay. Now, since uh, the modified Proctor test no, increases, no? Since it increases the compactive effort, okay, then it results in an increase in the maximum dry unit weight of the soil. No? Okay. So now this increase in the maximum dry unit weight is accompanied by a decrease in the optimum moisture content. Okay. And now, so the specifications given for Proctor test adopted by the ASTM standards, or that's the American Society for Testing Materials, as well as the AASHTO, okay, standards, with respect to the volume of the mold, okay, and the number of blows, okay, are generally those adopted for fine grain soils, take note, which passes through the US number for sieve. If you recall, this is I think 4.75 no, millimeters diameter sieve. Okay. Now, under each test designation, okay, uh, between the standard Proctor test and the modified Proctor test, there are three suggested methods that reflect the mold size, the number of blows per layer, and the maximum particle size in a soil aggregate used for testing, such as what we see here. Okay, so with respect to ASTM D698, that is the standard Proctor test, as well as the ASTM D1557, that is the modified Proctor test. Okay. Now, for each of these type of Proctor compaction test, there are three general methods, okay, being prescribed. That's method A, method B, and method C. Okay. Now, for each method, okay, we have here the general description of the material. Okay, so for method A, the material considered uh, is only the ones passing the number for C. Okay, for method B, the ones being considered are the only ones that pass the 9.5 millimeter diameter sieve. While for method C, here you consider the ones or the materials passing the 19 millimeter sieve. Okay. Now, method A is normally used if 20% or less by weight of the material is retained on the number for sieve. Okay. Now, method B is used if more than 20% by weight of the material is retained on the number for sieve, and 20% or less by weight of material is retained on the 9.5 millimeter sieve. Okay. Now, method C is used if more than 20% by weight of material is retained on the 9.5 millimeter sieve, and less than 30% by weight of material is retained on the 19 millimeter sieve. Okay. Now, for the mold the dimensions, for method A and method B, it is just the same. But for method C, we use a larger diameter of mold. Okay. So with that, then method C will also have a larger volume as compared to method A and B. Okay. Now for the weight of the hammer, okay, in the case of the standard Proctor test, okay, so that's just this it's just the same for all methods. Okay, this is for ASTM D698, this part here. Okay, the drop height for the standard Proctor test is just the same. The number of soil layers is just the same. Okay, I hope you're seeing my cursor. And the number of blows per layer is just the same for method A and B, but for method C, the number of blows is 56 per layer. Okay. Now, in the case of the modified Proctor test, okay, wherein you now have the bigger hammer, no? Okay, as what we have seen. Okay, okay, this one here, the modified Proctor hammer, that's the bigger hammer. Okay, so in that case, the weight of the hammer is about 44.5 newtons, which is just the same for all methods. The drop height is the same for all methods. The number of layers is more than the standard test. Okay, this is 3 and this is 5. But for the number of blows, it's just the same for both method A and B for standard and modified Proctor test, just the same, as well as for method C for both the standard and the modified Proctor test. They have the same number of blows per layer. Okay. So then when you do a report, then you must specify if you are using ASTM D698, method A or method B or method C, or if you're using ASTM D1557, that's the modified Proctor test, either methods A, B, or C. Okay. Okay. Now, um, for granular soils, okay, for granulars, in the case of granular soils, these are the sands, for example, no? For example, sands, with less than 12% fines, okay? So again, when you say fines, these are usually the materials finer than the number 200C. That's the 75 microns, okay? Yeah, 75 microns, so that's the 0.075 millimeters, okay? I think one of you before asked or clarified these fines. Again, when you say fines, these are the materials finer than the number 200 or finer than the 75 microns or the 0.075 millimeters. Okay. So in that case, if the fines is less than 12%, okay, the relative density may be a better indicator for the end product compaction specification in the field. Okay. Now, based on laboratory compaction tests on 55 clean sands, so when you say clean sands, that means you have less than 5% finer than the number 200 sieve. Okay. Now, then this guy, Patra, yeah, did some research, plotted the results of these clean sands, and so he was able to derive an empirical formula for the relative density, okay, with respect to D50, no? Where D50 is what you call the median grain size, which you can get from the grain size distribution curve. Okay. And then D sub R here is the maximum relative density of compaction achieved with a particular compaction energy. May it be standard compaction energy or modified compaction energy. Okay, where A and B here, A times D50 to the power negative B, where A and B here is given by these equations with respect to the compaction energy. Okay. Okay. Now, now in the field, we have different types of compaction equipment. Okay. Now, most of the compaction in the field is done with rollers. Okay. And then here we have the four most common types of rollers. We have the smooth wheel rollers, as mentioned earlier, or the smooth drum rollers. Okay. Then we have the pneumatic rubber tired rollers, the sheep's foot rollers, and the vibratory rollers. Okay, so let's try to discuss each one. Okay, now for the smooth wheel rollers, such as this one here, I think if you are into construction, then you normally have this equipment. If you are here to horizontal construction, for example, you normally have this equipment. Okay, the smooth wheel roller. Okay, for those into construction. Okay, so the smooth wheel rollers are basically suitable for proof rolling subgrades. Okay, for example, in roads, no, in road constructions, there's what you call as the subgrade, the subbase, and the base course, for example. Okay, so when dealing with the subgrades, for example, the smooth wheel rollers are suitable with this one, and also for finishing operation of fields with both sandy and clay soils. No? I mean, with both granular and cohesive soils. Okay. Now, these rollers provide 100% coverage under the wheels with a ground contact pressure as high as about 310 to 380 kilopascals, no, or just kilonewtons per square meter. Now, now the smooth wheel rollers are not suitable for producing high unit weights of compaction when used on thicker layers. Okay, thicker layers. Normally in thicker layers, sometimes we can use the dynamic compactors. No? Okay, dynamic compactors. I think we have done that in the CCLX project. Okay, these dynamic compactors. Now, new for the pneumatic rubber tired rollers. Okay, now these are better in many respects than the smooth wheel rollers. Okay, now these are usually are heavily loaded with several rows of tires, wherein each tire is closely spaced, say 4 to 6 in a row. Okay, such as this one here. Okay, this is a pneumatic rubber tired roller. Okay. Now for this one, the contact pressure under the tires can range from 600 to 700 kilonewtons per square meter, and they produce about 70 to 80% coverage, no? Because you notice there are some spaces here in between. Okay, unlike this smooth wheel roller, which is there are no space, so that's 100% coverage. So for this pneumatic rollers, okay, they can be used for both sandy and clay soil compaction. Okay, so the compaction is achieved by a combination of pressure and kneading action. No? When you say kneading action, just like when you are baking, no? Okay, you're trying to roll the dough, no? For the bread. No? That's a kneading action. Okay. Now, in the case of sheep's foot rollers, okay, these are actually drums with a large number of projections. Okay, the area of each projection may range from about 25 to 85 square centimeters. Okay, such as this one here. Okay, this is a sheep's foot roller, and this one here are the projections. No? Okay, wherein each projection can have an area of say, yeah, 25 to 85 square centimeters. No? This one here, the area of each projection. Okay. Now, these rollers are most effective in compacting clay soils. Okay. Now, the contact pressure under the projections can range from 1,400 to 7,000 kilo pascals. Okay. Now, during compaction in the field, the initial process compact the lower portion of the lift. Okay. Normally, we have what you call as a loose lift thickness. Okay. Normally, we specify between 200 to 300 millimeter loose lift thickness. Okay. Depending on the client. Okay. So with that loose leaf thickness, then the lower portion of that leaf is usually compacted on the initial process. Okay, and then the compaction at the top and the middle part of the leaf thickness, okay, of that 200 to 300. No? Because normally we compact every 200 to 300 loose leaf thickness. No? Okay, some can have 500, normally it's 200 to 300. Okay. So the compaction at the top and the middle part of that leaf thickness is done at a later stage, no? At the later process. Okay. Okay. So yeah, so if you are compacting clay soils, then yeah, these sheep's foot rollers are most effective. Okay. Although in my experience here in the Philippines, we don't normally compact place. Okay, mostly just sands. But in other temperate countries, no, these four season countries, wherein the majority of their materials are clays, then yeah, this will be a more suitable equipment for them. Okay? Only in some of our projects that we have used these sheep's foot rollers, but in most cases we use the 10-ton uh, vibratory roller compactors, no smooth wheel roller compactors. Yeah. Now, speaking of vibratory, I have here the fourth one. Okay, wherein vibratory rollers are extremely efficient in compacting granular soils, no, such as gravels and sands, for example. Okay. Now, vibrators can be attached to either a smooth wheel roller. Okay, it can be attached here, or it can be attached here, or it can be attached here. Okay, yeah. Um, to provide, and that is to provide vibratory effects to the soil. Okay, so normally we have this off-center rotating weights. Okay, wherein as this roller moves, now this one will also move this um, two off-center rotating weights. They will also move, which will cause a vibration as the roller will also move. Okay, so that will cause a vibratory effect. Okay. Now we also have the handheld vibrating plates, which can be used for effective compaction of granular soils over a limited area. Okay. Uh, Now, these vibrating plates are also gang mounted on machines. Okay. Then we normally use them, for example, when we um, um, do embankments, for example, or when we do mechanically stabilized earth walls. Okay. Or reinforced soil slopes are reinforced by geosynthetic materials. Normally on the corner this can no longer be reached by the normal compaction equipment such as just what we have mentioned earlier. So let's say on the remaining 1 meter, for example, from the edge of the slope or the embankment, then we normally just use the vibrating plates, no, to compact these areas, yeah, because it's very important to compact the edge corners of an embankment slope or a natural slope or a field slope. Okay, in the case of an mechanically stabilized earth wall, for example, or a reinforced slope, for example. This one I discussed in the masteral degree. Okay. 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 Now, in most specifications for earthwork, okay, the contractor is instructed by the client, okay, to achieve a compacted field dry unit weight of 90 to 95 percent of the maximum dry unit weight determined in the laboratory by either the standard or the modified Proctor test. Okay. Now this specification um, is what we call the relative compaction, which can be expressed by this formula here in percent, wherein the relative compaction is equal to the dry unit weight derived in the field over the maximum dry unit weight derived in the laboratory. No, just same as what we have discussed earlier, okay, multiplied by 100. Okay. Uh, Now, for the compaction of granular soils, specifications sometimes are written in terms of the required relative density, no? Okay, or the required relative compaction, such as this one here. Okay? Now, relative density as compared to the relative compaction is defined by this formula here. No? So please don't confuse the relative density, that's D sub R, to the relative compaction, which is capital R. Okay? Where the relative density is defined as the difference of the dry unit weight derived in the field. Okay, so later on we'll discuss how to determine this one. Minus the minimum dry unit weight derived in the lab over the difference in the maximum dry unit weight and the minimum dry unit weight derived in the lab multiplied by the ratio of the maximum dry unit weight derived in the lab over the dry unit weight in the field. Okay. Now, if you don't want to do this, then you can also do this if you like. No? Okay. Yeah. The relative density. But this one is an empirical formula. This one is derived from laboratory test. Okay. So sometimes when you do geotechnical investigation, sometimes we specify to determine in the lab the maximum and the minimum uh, dry unit weights, no? Or the unit weights. Okay. Maximum, minimum moist unit weights, then you have the moisture contents, then you get the maximum and minimum dry unit weights. Okay. So if we try to combine these two equations, okay, 6.19 and 6.20 in your book, okay, then just do some algebraic manipulations, we can see that the relative compaction can be related to the relative density um, using this formula here, where R sub 0 is defined as the ratio of the dry or the minimum dry unit weight over the maximum dry unit weight. Okay, that's R sub 0. Yeah. Okay, so now let's try to determine this one here. Sorry, where's my cursor? Uh, Sorry about that. Okay, okay. So let us now try to determine the dry unit weight in the field. Okay. Now, to do that, we have what we call as the sand cone method. That is ASTM D1556. Okay, the sand cone method. Now, for this method, we have what we call a sand cone device, which consists of a glass or plastic jar with a metal cone attached at its top, such as this one here. If you can see this one here, this is now a glass jar filled with we call it Ottawa sand um, in in Canada, no? For example, Ottawa in Canada, in Ottawa Sand, and then we you have a sand cone, no, being attached here. Okay. Okay. Now, in that device, the sand cone device, the combined weight of the jar plus the cone plus the sand filling the jar. Okay, let's try to designate that as W, capital W sub 1. Okay, so the total weight, the initial total weight. So then we go to the field, okay, after we do a compaction. Okay, then we want to test, no, how compacted it is. We go to the field, okay, and then we try to dig a small hole in the compacted area. Okay, um, and then we we excavate, no? We excavate the hole, okay, and then we try to weigh the moist soil from that hole, okay. Um, then we try to uh, consider that as W sub 2, okay. That's the weight of the moist soil excavated from the hole, okay. You excavate the soil, bring to the lab, the weight, okay, and then in the lab, you can also oven dry it to determine its moisture content, okay? In such a way that once you now have the weight of the moist soil excavated from the hole which you um, excavate in the compacted area, okay? So then from there, we can determine the dry weight of the soil. That's W sub 3, okay? That's the dry weight of the soil, okay, where the dry weight of the soil is now equal to the the moist uh, weight of the excavated soil over 1 plus the moisture content, okay, derived in the laboratory. Okay. Now, after the excavation of the hole, the cone with the sand-filled jar attached to it is then inverted. Okay, and then it's placed over the hole, no? Just like this one here. No? Okay, so we invert this one, and then we allow the sand to fill the excavated hole. Okay, okay. So then, okay, so sand is allowed to flow out of the jar to fill the hole and cone. Then after doing that, the combined weight of the jar, the cone, and the remaining sand in the jar is then being measured again, okay, because this is already being reduced, no, after filling the hole. Okay, then we now call that as a capital W sub 4 in such a way that if we subtract W sub 4 from W sub 1 will give us capital W sub 5, which is now the weight of the sand needed to fill the hole as well as the cone. Take note, no? Okay, so that's uh, the weight of the sand that would fill the hole plus the cone, no? This one here, okay? Yeah. Okay. Okay. So then you now have a W sub 5, okay, which is now a W sub 1 minus W sub 4. So then the volume of the excavated hole can then be determined by this formula here with W sub 5 minus W sub C over the uh, the dry. unit weight of the Ottawa Sun. Now, of this W sub C, which is the weight of the sun to fill the cone only. Okay, that's the weight of sun to fill the cone only. And then you have here the dry, okay, the dry unit weight of the Ottawa sun being used. Okay, these two parameters here are actually determined from the calibration done in the laboratory. No? So these are done. These are predetermined in the lab. Okay. Yeah. So then you now have the weight of the soil. Okay. In from the excavated hole. Then you have the volume of the excavated hole. Where's that weight again? Okay. Okay. That's yeah. So this is now the weight, no? That's the dry weight of the soil. Okay, the dry weight of the soil in the hole. Okay, that's W sub three, and then you have the volume of the hole. Then that gives you the dry unit weight of compaction made in the field. Okay, yeah, by applying this formula. Okay. Okay. Now, aside from the sand cone method, you also have the rubber balloon method, which is ASTM D2167. Okay. Now, for the rubber balloon method, a test hole is made. Okay. And the moist weight of soil is removed from the hole. Okay. The same as what we do in the sand cone method. And then the moisture content is also determined. um, However, the volume of the hole here is determined by introducing into it a rubber balloon filled with water from a calibrated vessel from which the volume can be read directly. Okay. So the dry unit weight of the compacted soil can still be determined by using this equation. Okay. Still the same. Okay. But only that we use a rubber balloon filled with water, okay, wherein that is being um, taken from a calibrated vessel. No? I, I think for the calibrated vessel, this is an example of that one or a figure of that one, okay, for the rubber balloon method. Okay. Now, we also have what we call the nuclear method. Okay. So, for the nuclear method, we have what we call as nuclear density meters, which are often used for determining the compacted dry unit weight of the soil. Okay. Now, the density meters operate either in drilled holes or from the ground surface. Okay. Now, this method uses a radioactive isotope source. Okay. Now, the isotope gives off gamma rays that radiate back to the meter's detector, wherein dense soil absorbs more radiation than loose soil. Okay. Now, this nuclear density meters measures the weight of wet soil per unit volume and the weight of water present in a unit volume of soil. Okay. So it automatically reads it. Okay. So there's no more measurement in the lab. No? It's being automatically being read by equipment. Okay. And then the dry unit weight of compacted soil can then be determined by subtracting the weight of water from the moist unit weight of the soil, such as the one we see here. No? So this is an example of a nuclear density meter. Okay. Now, some construction companies sometimes use this one, no? Okay, the nuclear density meter, because this is quite fast to do during construction, especially when you have a very tight schedule, and you cannot afford to wait for the results in the lab. Okay, so sometimes these things are being implemented for these equipments. The only concern in this equipment is that it gives radiation. Okay, so it has some health hazards, so that's why not everyone can easily operate this equipment. Okay, I think you must have some sort of a license to operate it. Then you have to wear some protective gears to operate it, to avoid these health hazards, because this is a nuclear approach. Okay. Yeah. Just to minimize exposure to radiation. Okay. Okay. Now, in doing compaction, okay, um, we also have a concern with respect to the presence of organic materials in the soil. Okay, because these organic materials, okay, I think we have already classified them uh, last meeting. Okay, for organic materials. Now, when you have organic materials, they normally reduce the strength of a certain material if these are found within it. Okay. Now, in many cases, soils with a high organic content are generally discarded as a fill material. Okay. Sometimes in some projects we specify to try to determine the organic content as well. Okay. There's some lab tests for that. Okay. Now, however, in certain economic circumstances, wherein you don't have a choice. Now, slightly organic soils are used for compaction. Okay. Now, some organic soils are desirable in many circumstances, such as for agriculture, desertification, mitigation, and urban planning, for example. Okay, wherein the high cost of waste disposal have sparked an interest in the possible use of waste materials. Okay, such as bottom ash obtained from coal burning, copper slag, paper mill sludge, shredded waste stars mixed with inorganic soil, and so forth in various landfill operations. Okay? Yeah, such as the use of waste materials, which is one of the major trusts of present day environmental geotechnology. Okay, so this is what we call a field called environmental geotechnology. Okay? Now, a certain guy named Franklin in 1973, he conducted several laboratory tests to observe the effect of organic content on the compaction characteristics of a soil. Okay. Now, in the test program, various natural soils and soil mixtures were tested, okay, such as this one here, okay, wherein this is now the graph of the maximum dry unit weight with respect to the organic content. Okay. And then here we see two results. This one here is from an oven dried sample, and this one here is from an air dried sample. Okay. Okay. Now, in that plot, okay, when the organic content exceeds 8 to 10%, the maximum dry unit weight of compaction decreases uh, rapidly. Okay. Now, conversely, the optimum moisture content for a given compactive effort increases with the organic content. So, if you see here, the maximum dry unit weight decreases with respect to the increase in organic content, while the optimum moisture content, okay, would increase with with increasing organic content. Okay, so that's what he found out. Okay, okay. Now, aside from that, the maximum unconfined compression strength, which we will discuss later when you go to shear strength of soils. Okay, the maximum unconfined compression strength obtained from a compacted soil with a given compactive effort also decreases with an increasing organic content of a soil. Okay. So yeah, based on these results here and here, they found out that soils with organic contents higher than about 10% are undesirable for compaction work. Although in practice, I think we specify um, a number lower than 10%, I think. Yeah, yeah, we specify a lower amount, no, for the organic content. Okay, that's in practice. Okay, okay. So in the next table that I will in the following table that I will show you, it provides a general summary of the evaluation of various types of soils as a fill material as they relate to the roller type, the maximum dry unit weight of compaction based on standard Proctor test and the compaction characteristics. Okay. Now, according to this guy source in 1979, uh, he observed that the compressibility and the expansion characteristics on compacted soils are depending on the type of soil. Now, for example, when you have well-graded gravels or poorly graded gravels, as well as well-graded sands and poorly graded sands, okay, if you try to recall these symbols, these US symbols, USA symbols we had last meeting, okay, so the compressibility and expansion characteristics for this type of soils are practically none. Okay, but for the silty gravel, clay gravels, silty sands, and clayey sands, okay, you have a slight effect there. Then for a low plasticity silt, M means silt, a low plasticity silt, okay, there's a slight to medium effect for compressibility and expansion characteristics. For the high plasticity silt, okay, you have a high effect, highly compressive and highly expansive. And then for the low plasticity clay, you have medium effect. And while for the high plasticity clay, which we don't like, okay, you have a very high effect on compressibility and expansion characteristics. Now, for example, in the case of a high plasticity silt, or we also call it is the elastic silt, as well as the high plasticity clay, which we also call the fat clay, normally the compressibility issue or the compressibility concern is when you have these materials found below the ground water level, okay, in the field, okay, which we usually measure uh, during the drilling operations. While the expansion characteristics is a behavior of these materials when such materials are above the ground water levels. Okay, so that's the main difference. So it depends on where your material is located, whether it is above or below the groundwater level. And this I discuss in more detail in the masteral degree. Okay, wherein expansive soils and collapsible soils are problematic soils above the groundwater level. Okay. Normally, when we prepare geotechnical reports, aside from giving the allowable bearing capacities of the soil, as well as the pile capacities of the soil with respect to either bored piles or driven piles, we also make geotechnical assessments such as the determination of the expansive soils, okay, with respect to your soil layer depths, okay, in that particular area, as well as soil collapsibility, as well as liquefiable soils. So these are quite problematic with respect to construction. Okay. Okay. So as mentioned earlier, we now have here the different types of fill materials. Okay. If you're seeing my cursor, we now have here the different type of fill materials. So either G is gravelly, S is sandy, okay, M is silty, and then C is clay material. Okay. So depending on the type of material, then you now have here the different rollers that is well suited or highly suggested when you use these materials in the field. Okay, so then with these materials, when you compact them using these equipments, then these are uh, the maximum dry unit weights, okay, as determined from the standard Proctor compaction test for these materials, okay, these values here. So that means if you are required by the client to achieve 90 to 95%, okay, then that means using these equipments in the field, okay, you must be able to achieve about 90 to 95% of these values as determined by the standard Proctor compaction test. Okay. So here, just to take note, if you are using well-graded gravels or poorly graded gravels, then the rubber tire or the steel wheel rollers, the vibratory effect, is best suited. While if you have a high plasticity clay or a fat clay, we also call it a fat clay, then the sheep's foot roller is highly suggested. Okay. So with respect to compaction characteristics, okay, so these materials here are generally fair to good, okay, generally fair to good, okay, while these materials here are generally poor to good with respect to compaction characteristics. And yeah, we also don't usually like these materials as a fill material, okay, because it has less drainage characteristics. We always like the higher permeability or the higher permeable materials. Anyway, we'll discuss permeability in the next topics. Okay. So the highly permeable materials are more recommended, no? As fill materials to avoid the build-up of poor water pressures. Okay. Okay. Now, several special types of compaction techniques have been developed for deep compaction of in-place soils, and these techniques are used in the field for large-scale compaction works. Okay. So among these techniques, the popular methods are the vibro flotation or the vibro compaction technique, the dynamic compaction technique, as well as the blasting techniques, although we try to avoid blasting as much as possible. Okay. Now, as of the moment, let's try to discuss this vibro flotation technique. Now, the vibro flotation technique for in situ densification or on-site, in situ means on-site, densification of thick layers of loose granular soil deposits. Okay. Now, this technique was first developed in Germany in the 1930s. Okay. And then later on, this device was used in the US after 10 years, okay, which involves the use of a vibrofloat unit called the vibrating unit, which is about 2.1 meters long. Okay, so this one here, okay, for example, this one here, this is now your vibrating unit. Okay. Okay. Now, this vibrating unit has an eccentric weight inside it, which can develop a centrifugal force, which enables the vibrating unit to vibrate horizontally. Okay. So if we again look at the entire assembly here, Okay, so this is yeah, but usually what we do on the site, no? Okay, we're in uh you yeah you try to um, compact, no? The soil using vibration, okay, or we call it the vibro compaction, okay, at deeper depths, no? Okay, then you can either do just a purely vibro compaction, or you can also add some materials, okay, due to the densification of the natural soil materials, okay. Mm. So in this case, that's vibro compaction. Now uh, in in construction, we also do what you call as the stone columns method, or the ram aggregate pier methods, no? With respect to ground improvement. Actually, this vibro flotation, the vibro compaction technique, is already under the topic on ground improvement techniques, no? Okay, which we normally discuss in the masteral degree, no? The different types of ground improvement techniques, such as the stone columns approach, and as well as the rammed aggregate pier approach. There are numerous ground improvement techniques that we do for problematic soils, depending on the type of material. But this is already discussed in the masteral degree. Okay, at least for the vibro compaction technique, you have here the zones where this technique are applicable. Okay, such as these zones here within the coarse sands and fine sands and gravels with minimal fine content. Okay, now in our experience, for example, when we do vibro compaction, such technique in improving the ground, such technique is very sensitive to the amount of the silt and the clay materials. So there's only some um, minimal percentage that is allowed, okay, for the vibro compaction technique to be effective in the field. Okay, so we had one project before wherein we tried to check if we can still do vibro compaction technique because it's always cheaper as compared to the stone column approach. Okay, but when we tested the soils and also doing a CPT test in the field, we found out that the fine content, okay, the fines content are way beyond the allowable for this vibro flotation or the vibro compaction technique to be considered effective, okay, to achieve a denser material, because we were dealing with loose materials up to depths up to 10 meters, no? Wherein yeah, it's already possible to do this normal compaction equipments. Okay, now as for the backfill material that you use, because here um, depending on the technique used, you might need to do some backfilling of materials. Okay. Now, for the quality of that backfill material, um, the grain size distribution of the backfill material is an important factor that controls the rate of the densification. Okay. So this guy, Brown, in 1977, has defined a quantity called the suitability number for rating backfills. No? That's S sub n, where S sub n is equal to this formula here, where you need the values for the D50, D20, and D10, no? Okay, which are the diameters in millimeter through which, respectively, the 50, 20, and 10% of the material passes. Okay? So the smaller the value of the suitability number, the more desirable the backfill material, no? Such as the ones here provided by Brown. Okay. So for example, if the suitability number is from 0 to 10, that means it is an excellent backfill. Okay, so that rating is an excellent backfill. But if the suitability number based on this formula here is already greater than 50, for example, then that is already considered an unsuitable material. Huh? Okay. Okay. So before I go to the some examples, do you have any questions or clarifications so far? So again, these examples are just taken from your book. No, don't worry about these examples. So for as long as you have the book, okay, the reference book, then you can just find all these things there. Okay, so if there are no questions so far, let me proceed. Okay, time check. It's now 8 o'clock. Okay. So here, in this example, we are given the laboratory test results of a standard proctor test. Here, no? Okay. So sorry. So here we have done yeah, about 6 points. Okay, about 6 points. Okay. So for example, you did this in the lab. You determine 6 points to be able to plot the compaction curve. Okay. So here we are asked to determine the maximum dry unit weight of compaction and the optimum moisture content. And then you're also asked to calculate and plot the dry unit weight before versus the moisture content for a degree of saturation equivalent to 80%, 90%, and 100%. So these are now, so for the 100%, that's the unit weight, the zero air voids unit weight. Okay. Considering this soil material has a specific gravity of 2.7. Okay. 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 So, um, so I think in this table here, the first, the second, and the fourth columns are the given. Okay, and while the third and the fifth columns are calculated. Okay, so from the given, we can calculate the moist unit weight. Okay, using this formula here, you just simply divide the weight of the soil by the volume of the mold. Then we get these values here. Okay. Then with these values, you have the moisture unit weight. Then you have the corresponding moisture contents. Then by using this formula here, then we can get the corresponding dry unit weights. Okay. And so then we plot the moisture content with respect to the dry unit weights. Okay, such as this one here. So we plot the 6 points. Okay. So then with the 6 points, okay, we're lucky to have quite a nice curve when we connect the points. And then here we can now see the peak of the curve, which will now give us the optimum moisture content, which is around 14%, and the maximum dry unit weight, which is around 17%. So to be accurate, it's around 17.15 kilonewtons per cubic meter, which is your maximum dry unit weight, and 14.4% for the optimum moisture content. Okay. And then for the for sorry. Then for this one, we are also asked to plot this one. Okay. For the dry unit weight with respect to the moisture content for 3 degrees of saturation, 80, 90, and 100%, where 100% is the zero air void unit weight. Okay. So then we can now use this formula as what we have discussed earlier. Okay, wherein you can replace
Naman si kay
this
pasok. Ayaw na stage ay bati na.
wherein you can
Cancel
replace.
stage.
Sorry, can someone mute yourself? Okay, thank you. Okay, so here you can try to replace the degree of
Kani
saturation.
siya nga duelist mo ra man siya sentinel nga duelist po.
I'm sorry, can someone please? Okay, I can see, I
Sa
can
gampitan lang mong
hear
blind.
you.
Kaya mo may maka-benefit na mo.
Um, Sorry, I think someone is speaking. Okay, can you kindly mute yourself because everyone can hear you? Okay, thank you.
Ano tagaan man ta gold ay?
I'm not sure if you can hear me. Okay, can someone see who is speaking? Because I cannot seem to see because I'm in presentation mode. Okay, so I guess you're already on mute now. Okay, I can continue. Okay, thank you. Okay, so by using this formula here, okay, so we can try to replace this parameter S, the degree of saturation by 80%, 90%, and 100%. Okay, so if we substitute the degree, sorry, the specific gravity here, which is given, that's 2.7, and then you have the unit weight of water that's given, that's 9.81 kilonewtons per cubic meter. And then you have the corresponding water contents. Okay, that's, I think, this is given. Okay, this one here. Yeah? Okay, you have the corresponding water contents. Okay, so substitute it here. Okay, so this one, sorry. So this one substituted here. Then you substitute the unit weight of water. And then you substitute here the water contents, and then try to consider 80%, 90%, and 100%, which will then give you these corresponding values. Okay. So then you can plot the water content or the moisture content with respect to these values for an 80-degree curve, 90-degree curve, and 100% degree of saturation curve. Okay. So then if you go back, this is then now the plot of that 80 degree of saturation. Um, this one is for the 90 degree of saturation. This one is for the 100% degree of saturation, or the 100% is equivalent to the zero air void curve. So that means you notice here, for example, that the maximum dry unit weight and the optimum moisture content did not even touch the curve for the 80% degree of saturation. So that means that means it is not necessary that when you achieve the maximum dry unit weight, then you're achieving very near the 100% degree of saturation. Okay. That means the sample, after achieving the the maximum dry unit weight and the optimum moisture content, is still considered an unsaturated soil or a partially saturated soil. Okay, so that means you can no longer compact that material beyond these curves. Okay, so it depends on the material. Okay, yeah. So that's how we interpret these curves here. Okay. Okay. Um, okay. Yeah. Okay. So we have here another example wherein we have the laboratory compaction test results for a clay silt, okay, which are given here. Okay, again, this is just found in your book, this problem. And then this is okay. This is done in the lab. Assuming we already know how to do this from the previous example. Okay, wherein you have the moisture content and the dry unit weight, okay, as derived in the lab. And then following here, this one here, are the results of a field unit weight determination test, okay, probably done using the sun cone test method, performed on the same soil. Okay, okay. So we assume that we tested the soil from a source. Okay, we do a compaction test in the lab, and then we use the same soil, and then we try to fill it in the field. Okay, and then we try to do some tests no, in the field. Okay, yeah. So then these are now the data that we got in the field. Okay, yeah. So these are the calibrated values, and these are the values derived as what was being provided in the discussions earlier. Okay. So from this data, we are asked to determine the dry unit weight of compaction in the field as well as the relative compaction in the field. Okay. Sorry about that. Let me just, okay. So for the first one, we are asked to determine again, the dry unit weight of compaction in the field. Okay, so with that, we can calculate the mass of sand used to fill the hole and the cone. That's uh, that's this one, this value, and minus this value. No, no. Okay, that's the mass before and after use. Okay, then we can determine the mass of sand used to fill the hole, which is this value minus 0.545, where 0.545 is the calibrated mass of the Ottawa sand to fill the cone. Okay, so that gives us this one. Okay, so then we can determine, we can, sorry, we can determine the volume of the hole by dividing this value by the dry density of the Ottawa sand, which is given here, the calibrated value. Okay? So that gives us this volume of the hole, okay, in cubic meters. And then we also have we can also determine the moist density of the compacted soil, which is the mass of the moist soil. I think that's also given. Okay, that's this one. The mass of the moist soil from the hole. Okay, divide that by this volume of the hole, which gives us this one, the moist density. Okay. So from the moist density, we can get the moist unit weight by just doing some conversions. Okay. That gives us this value. Okay. And then once we now have the moist unit weight, are we given the moisture content? Okay. Yeah, we have the moisture content. Okay. So then just substitute it here in this formula that gives you the dry unit weight of compaction in the field, which is about 18.56 kilonewtons per cubic meter. Okay. So in actual, this is what you do. Okay. You determine, I mean, in actual practice, no, using sun cone method. Okay. So you determine this one. And then in the lab, you try to plot, no? You try to plot the compaction curve as derived from the lab data, okay? So then you can get the maximum dry unit weight, which is from this curve, for example, you were able to get a nice curve. You get 19 kilonewtons per cubic meter, okay? So then to determine the relative compaction, which is now the dry unit weight in the field over the maximum dry unit weight as determined in the lab, okay, that gives you 97.7%. Okay. So that means if the client is prescribed for you to achieve at least 95% or at least 90%, then that means you have done a good job. Okay, so because you have achieved 97.7%. Okay. Okay, so another problem here. Okay. Now, for a given soil, the following are the results of the compaction test. Okay, so again, let's assume we already know how to derive this in the lab. Okay, and then after compaction of the soil in the field by using sand cone test, okay, these were conducted in five separate locations. For example, you are constructing a road. For example, let's say a 1 kilometer road. Then every 200 meters, you have done sand cone test in the field. Okay, to try to check if you have achieved the required specifications. Okay. And then with the sand contest, you were able to determine the moisture contents, okay, as well as the moist density, no, which we presume we already know how to do from the second example. No? So this one from the first example, this one from the second example. Okay. Now, the specifications require that the field dry unit weight must be at least 95% of the maximum dry unit weight as derived from the lab. Okay? And then the moisture content um, for that specification in item A should be within plus minus 2% of the optimum moisture content. Okay? So normally in construction, normally this is also the range we specify. That the moisture content in achieving the required compaction specifications, the moisture content should be within plus minus 2% of the optimum moisture content derived in the lab. Okay? We also specify this in the geotechnical reports as well, no? For earthworks, no? In the earthwork specifications. Okay, so let us now try to check if this data here from the lab and from the field would satisfy these conditions. Okay, otherwise, you fail. Okay, your field compaction fails. Okay, for example, if you're the contractor, okay, you have done a horizontal project such as a road construction, then you were asked to derive this test. For example, I'm your client, then I ask you to achieve these requirements, then you fail, then yeah, you just simply have to redo the work. Okay, you redo everything, which means that if you're the contractor, then it will lose you a lot of money, okay? Because you have to redo the work again, okay, for not doing a good job. Okay. So let's see if you have done a good job. Okay. So for example, if you are the contractor, okay, and then I ask you to do this, I'm the client, then you try to calculate now. Okay. So first, let's try to determine the zero air void unit weight. Okay. Yeah. So, are we given the specific gravity? Okay, so let's assume that the specific gravity is given 2.72. Okay, so then we can prepare um, uh, a table, no? With respect to the given water content. We have the same, yeah, okay. That's this one, the moisture content with respect to the zero air void unit weight. Now, using this formula here, as discussed earlier, okay. And so with that, we can now plot this one here, the dry unit weight in the lab, as well as the zero air void unit weight. So this one here. So this is now the compaction curve, or that's the dry unit weight curve with respect to the moisture content. And then this one here is the zero air void unit weight curve. Okay. So again, the compaction curve must not lie to the right of the zero air void curve. Okay. Okay. Now, from these curves, okay, uh, let's see. Okay. From this curve, okay, it can be seen that the maximum dry unit weight, okay, let's say this is now the highest point of your curve. Okay, you're lucky you were able to get a nice curve. Okay, so the maximum dry unit weight is about 17.4 kilonewtons per cubic meter, and then the optimum moisture content is 16.8%. This one here. Okay, now so from there, we are asked, or the specification says 95% of the maximum dry unit weight. So what is 95% of 17.4? So 95%, if you're seeing my cursor, 95% of the maximum dry unit weight is about 16.54 kilonewtons per cubic meter. So that means none of the test points 1 to 5, okay, none of these test points should go below this value here, which is 95% of the maximum dry unit weight. Okay. And then for all derived values in the field, their corresponding moisture contents must not exceed plus and minus 2% from the optimum moisture content, which is about 16.8%. So 16.8% optimum moisture content plus minus 2% will give you 14.8 to 18.8%. So that this is for the 14.8 and this is the 18.8%. Okay. So that means um, uh, point one, the test point one has passed. Okay, we're good there because it is above 95% of the maximum dry unit weight and the moisture content. Okay, so you have this one. Huh? Okay, this one. Uh, you have the corresponding dry unit weights derived from here. Then you have the corresponding moisture contents. No? So we plot each one here. Okay, so this is the plot for point one. So that's above, sorry, that's above the 95% and it's within plus minus 2%. So location one is okay. Then location two is also okay. It's within the specified moisture content range. Again, in practice, this is really the specifications that we use, plus minus 2%. Okay. Also in the technical reports we prepare, it's really plus minus 2%. Then, yeah, it's also above 95%. Okay. So this one here, it's above 95% of the maximum dry unit weight. Okay. And then for item three, okay, okay. For item three, you are just at the borderline, so still okay. Okay, still acceptable. But for item four, okay, while you are within the moisture content range, but you're already below the specified 95% specification. Okay, so that means point four has failed. Now for point five, okay, there seems to be an error here because it is the location is beyond. Okay, it's beyond the zero air void curve, and it is also beyond the optimum moisture content specification. Although it is above the required um, dry dry unit weight. Okay, so again, it is not enough that you are above the dry unit weight. Okay, you must be within the optimum moisture content, and then you must not exceed the zero air void curve. Otherwise, there's some error in your reading. That's how we interpret it. Okay, so that means you failed in test point four and test point five along, for example, along the 1 kilometer stretch of road that you have constructed, if you are the contractor and I'm the client, then with this result, I will be forced to tell you to redo the construction work. Okay, and that will lose you a lot of money because maybe you did not listen during my lecture. Okay, so that's why it's important to understand these things, especially when you do this in the actual work, especially if you are the contractor. Okay, and I am the client. Okay, okay, okay. So I think we have two more problems or examples. Okay. So here for this problem, you have a sand with 4% of finer than number 200 sieve. Okay. So here you're just asked to estimate the maximum relative density of compaction that may be obtained from a modified Proctor test with a given D50 equal to 1.4 millimeters. Okay. So, okay, so for the modified Proctor test, okay, you have here the modified compaction energy equivalent to this one, which you can calculate yourself, actually. Okay. So, using the empirical formula which we derived, or which we shown earlier, okay, then here the A and B can be determined with this corresponding com compaction energy, this one here. So just so we substitute it here in these two values. That will give us the values for A and B. Okay, so substitute these values here in this equation, and then 1.4 is your D50. Okay, yeah, equal to 1.4 millimeters. So that means here um, we have the corresponding relative density for that material equal to 83.6%. Okay, so 100% is also, of course, the perfect one. Okay, yeah. But I think a relative density of 83.6% is already considered dense. Okay, a dense material. That's already quite good. I think at least 75%, I think that's already a desired relative density in the field. Okay. Okay. Now another example. Okay, time check. We're almost time. Okay, let me just discuss this last example. Okay. Now here you are given the details for the backfill material needed to be used in a vibro flotation project or a vibro compaction project, wherein you now have the diameters for the D10, D20, and the 50. Okay. So then we are asked to check if we have a good backfill material, okay, to be used for our project. Okay, for example, you are the vibro compaction contractor, for example. Okay, so then from the formula, the suitability number S sub n is given by this formula here. You just simply substitute these values, which you can derive from the grain size distribution curve, which we discussed before. Okay, just substitute it here. Okay, that gives you a suitability number of 6.1. I think if you recall the table earlier, I think from 0 to 10 gives you an excellent rating. That means this material can be well compacted with your vibro compactor equipment or your vibro flotation equipment. Okay, so that means when we do ground improvement works in actual practice, these are quite sensitive to the material specifications. Otherwise, you cannot achieve the required ground improvement, okay, or the required density that is being specified by the client, and that is always challenging in actual construction. Okay, In my experience, we have done quite a number of ground improvement works. Okay. We perforated vertical drains in the Manila South Harbor, for example. We did some vibro compaction techniques, some stone column techniques in some of our power plant projects. Okay. And we also did jet grouting techniques. Okay. We did that for a project with ABS-CBN. Okay. We were building this this very high-tech studios before, okay, for the artists. Okay. So we also did some ground improvement works there. Okay. So um, in any ground improvement technique that you do in the field, these are always quite sensitive with the type of material you are dealing with, as far as my experience is concerned. Okay. Okay. So let's see. Okay. Yeah. I think that's the last slide. Okay. So do you have any questions so far? We are just on time. Okay. So maybe can have 5 minutes for questions, say if you have some questions or clarifications.